Imagine a whisper of verdant green, a shimmer of sapphire blue echoing from an impossible distance. Now project that echo across a chasm of 1,400 light-years to a world that hums with the promise of life, a cosmic island adrift in a sea of stars, 1,400 light-years. This is the staggering, almost crushing expanse that separates us from Kepler-452b, a celestial twin so hauntingly familiar that scientists have dubbed it Earth's older cousin. It's a world where the sun might paint a sky we recognise, where oceans could glisten, yet remains forever beyond our grasp. What profound cosmic twist is this? To discover a veritable paradise, a planetary mirror, only to confront the immutable laws of physics that render it an eternal, unattainable dream. Together, we will embark on an extraordinary journey of scientific simulation. If you're captivated by the universe's grandest mysteries, like this video, subscribe to our channel for more journeys into the unknown, and share your thoughts on Kepler-452b in the comments below. Prepare yourselves, we begin. For millennia, humanity gazed at the night sky, charting the familiar wanderers of our own solar system, yet always wondering if worlds like our own existed beyond the sun's dominion. The question of other Earths, once confined to the realm of philosophy and science fiction, began its slow, arduous transition into verifiable science at the dawn of the 21st century. Early ground-based telescopes unveiled a startling menagerie of exoplanets, mostly gas giants orbiting too close to their stars, offering tantalizing glimpses but rarely the promise of a true terrestrial sibling. The instruments were crude, the signals faint, and the quest for a world where life could thrive remained largely a fervent hope. Then, in 2009, NASA launched a mission that would redefine our cosmic perspective, the Kepler Space Telescope. Unlike its predecessors, Kepler wasn't designed to dart from star to star, observing fleeting phenomena. Instead, it was a dedicated sentinel, a cosmic eye fixed unblinkingly on a single, vast patch of sky in the constellations Cygnus and Lyra. Its sole ambitious purpose was to search for Earth-sized planets, orbiting other stars within their habitable zones, the precise regions where temperatures are just right for liquid water, the essential solvent for life as we understand it, to pool on a planet's surface. Kepler accomplished this monumental task by employing a remarkably elegant principle, the transit method. Imagine a distant star, a pinpoint of light billions of miles away. If a planet by chance passes directly between that star and Kepler's sensitive photometers, it casts a tiny shadow, momentarily dimming the star's light by a minuscule yet measurable amount. It's akin to detecting the brief, almost imperceptible flicker of a distant lighthouse as a moth flits across its beam. The regularity of these dips in brightness reveals the planet's orbital period, while the magnitude of the dimming provides a clue to its size relative to its star. This subtle, repeated cosmic ballet became Kepler's language, a silent symphony of distant worlds revealing their existence. Through years of relentless observation, Kepler's detectors collected an unprecedented cascade of data, a celestial treasure trove of photometric readings from over 150,000 stars. Each star's light curve, a graph charting its brightness over time, was meticulously analysed by algorithms designed to flag the characteristic dip of a transiting planet. The sheer volume of this data, coupled with the precision required to detect such minute variations, represented a triumph of engineering and computational science, pushing the boundaries of what was previously considered observable. Among the thousands of planetary candidates unearthed by Kepler's tireless gaze, one particular signal began to stand out with increasing clarity and profound significance. Orbiting a star designated Kepler-452, located some 1,400 light-years away within the constellation Cygnus, a planet repeatedly dimmed its parent star with an almost uncanny regularity. Over multiple orbital cycles, the dips maintained a consistent depth and duration, eliminating the possibility of stellar flares, sunspots, or other astronomical noise. This consistent rhythmic dimming was the unmistakable signature of a world, a solid body, circling its star with a dedication that hinted at a stable, long-term existence. The initial data that emerged from this signal was nothing short of astonishing, igniting a fervent hope that resonated across the scientific community and captivated the public imagination. Kepler-452b, as it was designated, completed an orbit around its star every 385 Earth days, a period strikingly similar to our own planet's 365-day year. This orbital resonance immediately placed it squarely within its star's habitable zone, a celestial Goldilocks sweet spot where conditions were neither too hot nor too cold, but precisely within the range where liquid water could persist on its surface. The implications were immediate and electrifying, a world so far away, yet so potentially similar. Further analysis painted an even more compelling picture. Kepler-452b was estimated to be about 1.6 times the diameter of Earth, classifying it as a super-Earth, a planet larger than our own, but still rocky and potentially solid, distinct from the sprawling gas giants that dominate so many other exoplanetary systems. This size suggested a substantial mass, and, crucially, the gravitational pull necessary to retain a robust atmosphere. The combination of its near-Earth-like orbital period, its position within the habitable zone, and its terrestrial-like size made it, at the time of its discovery in 2015, arguably the most Earth-like exoplanet ever identified, prompting NASA to announce it as Earth's older, bigger cousin. To quantify this extraordinary resemblance, scientists employed the Earth Similarity Index, or ESI, a metric that combines parameters like radius, mass, surface temperature, and orbital characteristics into a single value, with Earth itself scoring a perfect 1.0 Kepler-452b, registered an impressive ESI of 0.83, a number that placed it in an elite tier among known exoplanets, a startling testament to its potential. It wasn't just another distant rock, it was a profound echo of our own world, a beacon of possibility shining across the vast, dark ocean of space. But what truly fueled the imagination, transforming this distant data point into a potential living world, was the age of its parent star, Kepler-452, this G2-type yellow dwarf, almost identical to our own Sun in spectral class and luminosity, was estimated to be approximately 6 billion years old. This makes it a staggering 1.5 billion years older than our Sun. This extended lifespan carries monumental significance for the prospect of life. On Earth, it took billions of years for single-celled organisms to evolve into complex multicellular forms, and then millions more for intelligence to emerge. Kepler-452b, with its stellar parent offering a 1.5 billion-year head start, theoretically provided an immensely prolonged evolutionary canvas for life to flourish, diversify, and perhaps even achieve a level of complexity far beyond our own. The implications were clear. If life had begun there, what wonders might have unfolded across such an immense span of cosmic time? This wasn't merely a potentially habitable world, it was a potential paradise, already ancient. Already possibly teeming with life that had journeyed through eons we can only just begin to comprehend. End of hook section. The very bedrock of Kepler-452b's tantalizing potential for life lies not on the planet itself, but within the colossal furnace of its parent star, Kepler-452. This celestial anchor, 1/400 light-years distant, is remarkably similar to our own Sun, a cosmic doppelganger that provides the stable, enduring conditions essential for a thriving biosphere. It is classified as a G2-type yellow dwarf, shining with a familiar golden hue, only about 11% larger in diameter than our own star. This spectral kinship is more than a mere classification. It's a profound indicator of stellar behavior, directly impacting the prospects for life on its orbiting worlds. Unlike the common, yet often treacherous, red dwarf stars that populate our galaxy, Kepler-452 maintains a placid, predictable demeanour. Red dwarfs, though numerous and long-lived, are notorious for their violent stellar flares and intense emissions of X-ray and ultraviolet radiation. Planets orbiting within their habitable zones often face a constant bombardment of deadly energy, an atmospheric stripping assault that can sterilize a world or make complex life's emergence an insurmountable challenge. Kepler-452, by contrast, offers a calm, consistent stream of light and heat, precisely the kind of astrophysical stability a developing biosphere needs to flourish without being repeatedly reset by catastrophic stellar outbursts. This unwavering stellar stability means that hypothetical plant life on Kepler-452b could, in principle, evolved to rely on photosynthesis akin to Earth's verdant greenery. Without the threat of intermittent deadly bursts of X-ray energy or extreme ultraviolet radiation, photosynthetic organisms wouldn't need to develop costly and energy-intensive biological shielding. The gentle, consistent glow of a G2 dwarf star provides a reliable energy source, fostering uninterrupted biochemical processes and allowing ecosystems to mature and diversify over vast stretches of time, rather than constantly struggling for survival against an erratic, hostile sun. But beyond its calm temperament, Kepler-452 possesses an attribute of monumental significance for the evolution of life: its astonishing age. Scientists estimate Kepler-452 to be approximately 6 billion years old, nearly 1.5 billion years older than our own Sun. This extended lifespan is not merely a curious detail, it represents a cosmic head start, an immense stretch of uninterrupted geological and biological time. On Earth, the journey from primordial chemistry to single-celled organisms and then to complex multicellular life spanned billions of years. The emergence of intelligent, tool-using species was the culmination of countless evolutionary steps, each requiring immense durations of stability. A star with a lifespan like Kepler-452 creates the ultimate stage for such a grand transformation. It is the bedrock of sustained habitability, providing the minimum requirement for a planet to preserve a life-friendly environment over geological timescales. Imagine the profound silence of eons unfolding, 1.5 billion years more than Earth has known, giving any potential life on Kepler-452b an unparalleled opportunity to evolve, adapt, and perhaps even achieve complexity we can barely conceive. This extended timeline suggests that if life emerged there at a similar pace to Earth, it could be far more ancient, more evolved, and potentially more advanced than anything known in our solar system. Adding another crucial layer to Kepler-452b's promising profile are its orbital characteristics. Its year lasts approximately 385 Earth days, a period that almost perfectly mirrors our own planet's orbit. This means its distance from Kepler-452 is strikingly similar to Earth's separation from the Sun, placing it squarely in the sweet spot of the habitable zone. It's not so close as to scorch its surface, nor so distant as to plunge it into a frozen wasteland. This orbital dance, so familiar in its rhythm, ensures that the planet receives a consistent, moderate amount of stellar energy, further stabilizing its climate and fostering conditions conducive to liquid water. Crucially, Kepler-452b is not tidally locked. This is a monumental advantage, distinguishing it from countless other exoplanets, particularly those orbiting the more common red dwarf stars. Tidal locking is a phenomenon where a planet's rotation period matches its orbital period, resulting in one side perpetually facing its star in eternal daylight, while the other remains trapped in endless night. Worlds like Proxima Centauri b, though within their star's habitable zones, often suffer this fate. Imagine a planet where one hemisphere is a blistering desert, scorching enough to boil away oceans, while the other is an icy wasteland. A frozen tomb where any water is locked away as ice. Such extreme conditions create catastrophic temperature gradients across the planet's surface, rendering the entire world largely inhospitable. The Terminator line, the narrow strip between perpetual day and night, might offer a fleeting sliver of temperate existence, but the overall environment would be one of brutal extremes. Kepler-452b, however, escapes this gravitational embrace. Its independent rotation allows heat to be distributed more evenly across its entire surface, moderating temperature swings between day and night and across seasons. This absence of devastating temperature gradients fosters a stable, temperate global environment, a vast and balanced stage where complex ecosystems could emerge and thrive over billions of years, adapting and diversifying without the crushing pressures of planetary-scale thermal imbalance. This freedom from tidal locking is not just an advantage, it's a profound opening, a critical piece of the puzzle that makes Kepler-452b a truly Earth-like world, far beyond merely being in the right place at the right time. With the benevolent gaze of its sun-like star Kepler-452 providing billions of years of stable energy, the next layer of Kepler-452b's potential unravels through its own physical characteristics. This world is no mere rock, it's a super-Earth, a designation that immediately sets it apart from both the smaller, barren terrestrial planets like Mars and the colossal gas giants that dominate our outer solar system. At approximately 1.6 times the diameter of Earth, Kepler-452b occupies a fascinating middle ground, hinting at a world that is rocky and solid, yet possesses a scale that could profoundly reshape everything we understand about planetary dynamics and the evolution of life. However, its larger size comes with a formidable consequence: immensely amplified gravity. While direct measurements of its mass are still estimates, sophisticated planetary models predict that Kepler-452b's surface gravity could be as much as 2.2 times stronger than Earth's. This is a staggering figure, a constant, pervasive force that would redefine existence on its surface. Imagine a world where every step feels like a monumental effort, where simply lifting your arm requires more than twice the energy, where the sensation of your own body is that of an immense continuous weight. This crushing gravity isn't just a physical inconvenience. It's a fundamental sculptor of the planet, influencing its very geology, shaping its atmosphere, and dramatically altering the trajectory of any biological evolution. The geological implications of such powerful gravity are immense. On Earth, the dynamic dance of plate tectonics, responsible for carving towering mountain ranges and vast chasms, is driven by the internal heat of the planet and the relatively lighter burden of gravity allowing crustal plates to move and buckle. On Kepler-452b, with gravity more than doubling, the very processes that uplift and erode terrestrial landscapes would be fundamentally constrained. Mountain ranges might struggle to reach significant heights, their colossal weight collapsing them under their own immense gravitational stress. Valleys and canyons might be shallower, broader, or formed by different mechanisms, as the forces required to create deep fissures would be amplified. The result would likely be a largely flatter, more uniform landscape than Earth's rugged topography, a world whose surface features are subdued, compressed, and smoothed by the relentless downward pull. Yet, this immense gravitational force isn't solely a constraint. It offers a critical advantage for habitability, the ability to retain a dense protective atmosphere. Smaller planets like Mars, with their weaker gravity, have struggled to cling to their atmospheric blankets, losing vital gases to the relentless pull of space and stellar winds. Kepler-452b's formidable gravitational grip, by contrast, acts as a powerful anchor, holding on to atmospheric gases with exceptional tenacity. This means a denser atmosphere, possibly richer in components vital for life, could persist for billions of years, creating a stable, long-term environmental buffer. Such a dense atmospheric blanket would be transformative. Firstly, it would act as a planetary thermostat, moderating extreme temperature swings between day and night. On worlds with thin atmospheres, heat rapidly radiates into space after sunset, leading to drastic drops in temperature. A thick atmosphere on Kepler-452b would trap and redistribute heat more efficiently, creating a far more stable and temperate climate across its surface. Secondly, this protective shroud would shield the surface from the harsh realities of space, intense ultraviolet and X-ray radiation from its star, as well as high-energy particles and micrometeoroids. This celestial armour is critical for the survival and stability of complex organic molecules, the very building blocks of life, preventing their degradation and offering a crucial environment for their assembly and evolution. It is a profound advantage, creating a sanctuary where intricate biological processes could unfold without constant existential threat. However, the delicate balance between abundant stellar energy and a thick heat-trapping atmosphere introduces a significant concern: the potential onset of a runaway greenhouse effect. While Kepler-452b's average surface temperature is estimated at a comfortable 80 degrees, 27, ideal for liquid water, it receives approximately 10% more stellar energy from its sun-like star than Earth does from ours. This seemingly modest increase, coupled with a potentially dense atmosphere rich in greenhouse gases like carbon dioxide, could tip the planet into a perilous thermal imbalance. The nightmare scenario, terrifyingly exemplified by Venus in our own solar system, involves a positive feedback loop. Increased temperature leads to more water vapor in the atmosphere, a powerful greenhouse gas, which traps more heat, leading to even more evaporation, and so on. If carbon dioxide levels accumulate too much, the excess heat could become irreversibly trapped, evaporating entire oceans and transforming the planet into a scorching wasteland. On Venus, surface temperatures are hot enough to melt lead, and its atmosphere is a dense, crushing blanket of CO2. Climate simulations suggest that if Kepler-452b's atmospheric CO2 concentration equals or exceeds Earth's levels, it could enter such a runaway state within a few 100 million years, a mere blink in the cosmic timescale, especially given its star's advanced age. This raises a fascinating yet sobering possibility that Kepler-452b might represent a cosmic version of Earth's deep past. Some researchers draw parallels to Earth's Mesozoic era, the age of the dinosaurs, a period when global temperatures were significantly higher and atmospheric CO2 levels far exceeded today's concentrations. In that ancient epoch, Earth was a greenhouse world, largely free of polar ice caps, with warm, shallow seas covering vast stretches of land, with its similar parameters, a larger, warmer super-Earth, receiving more stellar energy. Kepler-452b could be a living fossil, a primordial stage where ecosystems, if present, have developed under conditions long vanished from our world, offering a unique window into a possible future for our own planet, or a glimpse into a very different evolutionary past. It is more than just a planet in a prime location orbiting a stable star. It possesses physical characteristics that ignite profound questions about the delicate line between habitability and catastrophe. But to truly grasp its potential, we must look closer to its surface, where terrain, water, and perhaps even the earliest ecosystems may hold the next chapter of this extraordinary complex story. Now, let us turn our gaze from the planet's internal dynamics and stellar parent to its most immediate, thus enveloping feature, its atmosphere. This crucial layer, born from the planet's immense gravitational pull and refined by billions of years of geological and potentially biological activity, defines the very experience of standing on Kepler-452b. It dictates the colour of its sky, the quality of its light, and serves as the primary shield against the harsh realities of space, fundamentally shaping any potential biosphere. Given Kepler-452b's estimated 2.2 times stronger surface gravity compared to Earth, planetary scientists hypothesize a significantly denser atmosphere. This is a critical distinction. On Earth, our atmosphere extends hundreds of kilometers, thinning rapidly with altitude. On Kepler-452b, the powerful gravitational field would compress its gaseous envelope more tightly, ensuring that a greater mass of atmospheric particles remains closer to the surface. This increased density isn't merely an abstract number, it has profound implications for the planet's climate, geology, and most vividly, the visual experience of its environment. One of the most immediate consequences of a denser atmosphere would be its effect on light scattering. On Earth, our sky is blue because nitrogen and oxygen molecules preferentially scatter shorter blue wavelengths of sunlight. On Kepler-452b, with a greater density of atmospheric gases, this scattering effect could be amplified. However, the composition of that atmosphere also plays a crucial role. If, like Earth, it is rich in nitrogen and oxygen, the sky would likely appear a deeper, more saturated blue, perhaps even a brilliant indigo. As more blue light is scattered across a wider range of angles, but if other gases are abundant, particularly denser ones or those with different scattering properties, the sky could take on entirely different hues. A perpetually hazy lavender, a muted grey, or even a pale orange if aerosols or dust particles are prevalent. The presence of a substantial atmosphere is also directly linked to the Goldilocks temperature range observed on Kepler-452b. With an average surface temperature of 80 degrees, liquid water is theoretically stable. This moderate temperature isn't solely due to its position in the habitable zone, but equally to the atmospheric blanket's ability to trap and redistribute heat. Just as a heavy blanket keeps a sleeper warm, a dense atmosphere acts as a thermal regulator, preventing drastic temperature swings that would render life impossible. It absorbs incoming solar radiation during the day and slowly releases it at night, mitigating the extreme thermal gradients that plague planets with thin or no atmospheres. This constant, gentle warmth, maintained by a thick atmospheric shroud, is a hallmark of sustained habitability. Beyond temperature regulation, This dense atmosphere would serve as Kepler-452b's primary defense system, a protective barrier against the relentless assault from space. Despite Kepler-452 being a stable, sun-like star, all stars emit a continuous stream of charged particles known as stellar wind, along with occasional powerful bursts of ultraviolet and X-ray radiation. A thick atmosphere acts like a cosmic filter, absorbing and scattering these harmful energies before they can reach the surface, thus safeguarding any complex molecules or nascent life forms that might be trying to emerge or evolve. Without this protective blanket, the surface would be constantly sterilized, bombarded by radiation lethal to terrestrial biology. The atmosphere is, in essence, the planet's skin, shielding its delicate interior from the ravages of the cosmos. Furthermore, a dense atmosphere would offer significant protection against micrometeoroids and smaller asteroid impacts. On airless bodies like the Moon, every impact leaves a crater. On Earth, most smaller space debris burns up in our atmosphere, appearing as fleeting meteors or shooting stars. On Kepler-452b, with its even denser atmospheric shield, this protective effect would be amplified. Fewer impactors would reach the surface, meaning the landscape would be less scarred and the environment more stable, allowing ecosystems to develop and thrive without constant disruption from extraterrestrial projectiles. However, this very advantage, the atmosphere's density and its capacity to trap heat, brings us back to the looming threat of the runaway greenhouse effect. While a certain atmospheric density is beneficial, an overabundance of greenhouse gases like carbon dioxide, perhaps released through intense volcanic activity on a planet with a hotter core, could push the system past a critical tipping point. If the atmospheric composition became dominated by such gases, the thermal regulation would become thermal runaway. The 10% greater stellar energy received by Kepler-452b compared to Earth acts as a perpetual accelerant in this scenario. Even if the initial conditions were perfect, a subtle shift in the planet's carbon cycle, perhaps due to a lack of plate tectonics to recycle carbon, could initiate a cascade of warming. Oceans would begin to evaporate, releasing vast amounts of water vapor, itself a potent greenhouse gas, into the atmosphere. This would intensify the heat trapping, leading to more evaporation until all surface water is gone and the planet transforms into a superheated, barren world much like Venus. This delicate balance underscores a critical principle of planetary habitability. It's not enough to be in the habitable zone. A planet must also possess the right atmospheric composition and dynamics to maintain its temperate state over geological eons. The atmosphere of Kepler-452b is thus a double-edged sword, a dense protective blanket that fosters life's potential, yet one that carries the inherent risk of becoming an inescapable, suffocating shroud. Its colour, its density, its very breath tell a complex story of promise and peril, a testament to the intricate and fragile conditions required for life to not just emerge, but to endure. The sky above Kepler-452b could be a profound, vivid blue, a symbol of its vibrant potential, or it could be a hazy, oppressive veil foreshadowing a tragic, superheated fate. This atmospheric veil is the first true interface between the raw power of its star and the delicate potential of life below, a canvas painted with the very essence of its existence. Having explored the overarching characteristics of Kepler-452b's stellar parent and its planet-defining atmosphere, we now plunge beneath that dense, often indigo sky to envision the very surface of this enigmatic world. From the estimates of its temperature, atmospheric conditions, and the crushing weight of its 2.2 times stronger gravity, a distinct picture of its surface emerges, one dominated by sprawling shallow oceans, a global aquatic canvas that would profoundly shape its climate, geology, and the very trajectory of any life that might call it home. Imagine standing on a hypothetical shore, feeling the immense pull of gravity anchor you to the land. Above, the sun-like star, Kepler-452, hangs in a sky that, depending on atmospheric composition, could range from a deep, saturated blue to a hazy, almost violet hue. The air, thick and humid, would carry the scent of unfamiliar salts and the distant rhythmic sigh of waves. Before you, not vast, segmented continents, but an immense, unbroken expanse of water. Planetary science models suggest that Kepler-452b's formidable gravitational pull would make the formation of towering mountain ranges or profound abyssal trenches, akin to Earth's Grand Canyon or Mariana Trench, highly improbable. Under such persistent immense compression, tectonic activity, if present, would likely be subdued, limiting the planet's ability to push massive land masses upward or create deep rifts. The result? A largely flat, uniform landscape where water, if abundant, would spread broadly across the surface, forming vast, interconnected, shallow oceans rather than deep, isolated basins separated by towering continents. This scenario resonates with a profound echo from Earth's deep past, our own ancient Mesozoic era, the age of the dinosaurs. During that epoch, Earth experienced significantly higher global temperatures and atmospheric carbon dioxide levels. Our planet vast epicontinental seas, shallow oceans that spread across what are now continental interiors. On Kepler-452b, these conditions could be not merely replicated but amplified. We envision a world where the average surface temperature hovers around a balmy 80 degrees C, a perpetually warm, inviting environment where liquid water would be the dominant feature, extending horizon to horizon. The sheer scale and shallowness of these hypothetical oceans would not only sculpt the planet's appearance, but also profoundly influence its climate. Water, with its exceptionally high specific heat capacity, acts as a colossal thermal battery. It absorbs solar energy slowly during the day and releases it gradually at night, effectively moderating temperature swings. On Kepler-452b, global oceans would serve as an immense climate buffer, preventing the kind of devastating temperature gradients that plague tidally locked worlds or those with thin atmospheres. This natural ability to regulate temperature would foster an environment that is remarkably stable, temperate, and consistently conducive to life, creating vast, uniform habitats for aquatic organisms. Furthermore, the extensive presence of liquid water would be instrumental in regulating the planet's atmospheric composition, particularly in relation. Water is not only the universal solvent for biochemistry, but also a key player in the carbon cycle. If Kepler-452b possesses vast liquid water reserves and an active hydrological cycle, a continuous process of evaporation, condensation, burst, and precipitation, it could potentially sidestep the catastrophic fate of Venus. On Venus, carbon dioxide trapped heat, leading to the complete evaporation of oceans and the eventual loss of any chance for life. On Kepler-452b, a robust hydrological cycle could facilitate the dissolution of atmospheric CO2 into the oceans, where it could then be sequestered into sedimentary rocks, thereby regulating the planet's greenhouse gas levels. This delicate planetary feedback loop, driven by the abundance of water, would be its primary defense against transforming into a superheated inferno. These sprawling, shallow oceans would also create ideal conditions for photosynthetic life. Sunlight, crucial for energy production, would penetrate deep into the water column across vast areas. This would foster the widespread growth of plankton, algae, and other aquatic plant-like organisms, forming the foundational layer of any marine food web. Their presence would initiate robust nutrient cycling, drawing carbon dioxide from the atmosphere and releasing oxygen, potentially shaping the very breath of the planet. Such a vibrant marine biosphere, given the star's billions of years of stable output, could have reached unimaginable levels of complexity and diversity. This potential for a globally interconnected, warm, shallow ocean environment suggests a planetary incubator of immense proportions. The transition from sea to land, a monumental evolutionary leap that occurred hundreds of millions of years ago on Earth, could unfold on Kepler-452b on an even grander scale. Imagine the alien shores, gently sloping into vast, warm waters, providing countless transitional zones where life could gradually adapt to a semi-aquatic or fully terrestrial existence. This continuous, uniform coastline, unbroken by colossal mountain ranges, could have fostered a slow, deliberate migration of life from the comfort of the water to the challenges of the land, driven by the relentless pressures of natural selection over eons. The vision of Kepler-452b's surface, therefore, is one of a primeval, almost paradisiacal aquatic world. Warm, stable, and deeply interconnected, its shallow oceans would be a living testament to the power of liquid water as a catalyst and guardian of life. It's a compelling simulation of a world teeming with potential, a cosmic echo of Earth's vital past. yet one fundamentally reshaped by its unique gravitational and stellar context. It truly represents a second Earth, in terms of its potential to harbour a biosphere, a world that, through our scientific lens, appears breathtakingly vibrant and fertile. Yet, this idyllic image carries the haunting caveat: this vibrant, water-rich environment is exquisitely poised on a knife edge, its future perpetually threatened by the very stellar energy that nourishes it, making its lush, ancient beauty a spectacle we can only ever dream of reaching. With the immense, shallow oceans of Kepler-452b teeming with potential and a dense, protective atmosphere filtering the light of its ancient sun-like star, our imagination now turns to the most fundamental question. If life has indeed emerged on this distant world, what would its flora look like? How would the alien plants, the primary producers of any ecosystem, adapt to conditions that are both familiar and profoundly different from Earth's? The story of life on Kepler-452b, much like on Earth, would almost certainly begin in its water. The widespread shallow oceans, warm to an average of 80° and bathed in consistent light from Kepler-452, provide an ideal incubator. We might first imagine a thriving aquatic world, commencing with microscopic single-celled organisms, perhaps akin to Earth's earliest prokaryotes. Over billions of years, these could evolve into more complex multicellular life, mirroring the cyanobacteria and early algae that once dominated Earth's primordial seas. These organisms, forming the base of the food web, would harness the energy of their star through photosynthesis. Kepler-452's spectrum is strikingly similar to our Sun's, meaning it emits light across a comparable range of wavelengths. This is a crucial detail for hypothetical plant life. On Earth, plants appear green because they absorb red and blue wavelengths for photosynthesis and reflect green light. On Kepler-452b, if the primary pigments for light capture evolved similarly, perhaps using chlorophyll-like molecules, then vast expanses of the planet's surface, both aquatic and terrestrial, might indeed appear green. However, evolution is a master of optimization, and even subtle environmental differences can lead to dramatic variations. The denser atmosphere on Kepler-452b could scatter light differently, potentially altering the dominant wavelengths reaching the surface. Or, the slightly higher stellar energy input might favour pigments that absorb a broader spectrum of light, or even different specific wavelengths. This could lead to a fascinating array of colours for alien flora. Imagine leaves that appear deep blue, absorbing more of the redder light, or even black, efficiently capturing almost all incident radiation to maximise energy intake in a world where every photon counts against the immense gravitational burden. The hypothetical plant life could exhibit a wide palette of colours unseen on Earth, from fiery reds to deep purples, each hue an adaptation to its unique stellar illumination and atmospheric filter. As life on Kepler-452b transitioned from the water to the extensive flat land masses, the crushing 2.2 times stronger gravity would become the ultimate architectural challenge for any terrestrial flora. On Earth, trees like the Californian redwoods can soar over 100 meters, their vascular systems pumping water against a single G. On Kepler-452b, such towering structures would be incredibly difficult to support. The sheer weight of a tall trunk, coupled with the immense energy required to transport water and nutrients against 2.2 G, would necessitate radical adaptations. Picture alien shores and plains lined not with towering forests, but with strange, thick-stemmed plants. These would likely be low-lying, robust structures, perhaps sprawling outwards rather than upwards, mimicking Earth's ancient fern forests or vast, creeping ground covers. Broad, expansive leaves would be essential, not just for capturing every photon from Kepler-452's consistent light, but also to minimize the need for vertical growth. Their stems would be incredibly dense, perhaps reinforced with novel biological polymers designed for maximum structural integrity against the relentless downward pull. Some might even evolve hollow, yet reinforced structures, similar to certain grasses or bamboo, to achieve some height without becoming impossibly heavy. The very growth patterns would be dictated by gravity. Root systems would need to be exceptionally deep and widespread, anchoring the plants firmly to the ground, preventing collapse or uprooting in any wind currents. The biomechanics of water transport, sap flow, and nutrient distribution would demand highly efficient pressurized vascular systems capable of overcoming the amplified gravitational resistance. Perhaps some plants would develop symbiosis with subterranean fungi or microbes to assist in nutrient uptake, or evolve intricate capillary networks that rely on strong surface tension and osmotic pressures to defy gravity's relentless pull. Another fascinating adaptation might involve the life cycle of these plants. Reproduction could be optimized for ground-level dispersal, with seeds or spores being heavy and dense, designed to fall and quickly root rather than relying on wind dispersal. Or, conversely, some might produce incredibly lightweight, buoyant seeds, leveraging a potentially denser atmosphere for limited aerial distribution. The sheer longevity of Kepler-452's star, however, would have granted ample time for an astonishing array of solutions to emerge, each one a testament to life's incredible adaptability in the face of profound physical challenges. This vision of Kepler-452b's flora is not just a fanciful imagining. It's a scientific exercise in biomechanical constraints and evolutionary possibility. It demonstrates how the familiar process of photosynthesis, the very engine of life, would be expressed in forms utterly alien to our eyes, yet fundamentally comprehensible through the universal laws of physics and biology. These robust, gravity-defying plants would form the foundation of an entire ecosystem, transforming raw stellar energy into the biochemical fuel for all other life on this ancient, distant world. They are the silent, steadfast architects of Kepler-452b's biosphere, a vibrant, resilient tapestry of life woven under a sky of unknown colour, defying the crushing embrace of a heavy world. From the resilient, gravity-defying flora that would anchor Kepler-452b's ecosystems, our gaze naturally ascends to the animal life that would graze upon, hunt within, and traverse these ancient, heavy landscapes. The crushing embrace of 2.2 times Earth's gravity would be the paramount sculptor of all terrestrial fauna, fundamentally reshaping their anatomy, physiology, and behaviour in ways that would appear profoundly alien to our earthbound eyes. Any creature daring to venture onto the solid surface of this super-Earth would be an evolutionary marvel, a testament to life's relentless adaptability under extreme duress. The most striking characteristic of land animals on Kepler-452b would be their morphology. They would be built for solidity and stability, optimized for weight distribution rather than height or agility. Imagine creatures with short, powerful limbs, thick, dense bodies, and a low-slung posture, constantly battling the immense downward pull. Unlike the towering giraffes or slender gazelles of Earth, a high-gravity world would favour wide, sprawling forms that maximize contact with the ground, effectively distributing their amplified weight over a larger area. This body plan minimizes the leverage gravity can exert to topple them, making them appear almost pressed into the landscape. The internal architecture of these organisms, particularly their skeletal systems, would be radically different. On Earth, skeletons are designed for support, flexibility, and muscle attachment. On Kepler-452b, bones would need to be exceptionally dense and robust, perhaps containing novel, incredibly strong biological composites to withstand the continuous, overwhelming compressive forces. We might expect bones to be significantly thicker in proportion to body size, or even for an organism to evolve an external skeleton, an exoskeleton, providing unparalleled structural integrity, much like terrestrial arthropods on Earth, but on a grander, denser scale. Alternatively, some larger creatures might develop a system of internal, hollow but heavily reinforced bones, a compromise between strength and managing overall body mass. This balance between structural necessity and the immense energy cost of moving a heavy frame would be a constant evolutionary pressure. Musculature would also be profoundly enhanced. Every movement from the slightest twitch to a powerful stride would demand immense strength. Terrestrial creatures on Kepler-452b would possess incredibly dense and powerful muscle fibers, particularly in their legs, torso and neck, optimized for short bursts of immense force rather than sustained rapid motion. Their locomotion would likely be slow, deliberate and powerful, perhaps akin to a heavily armoured tank moving across rough terrain. Many species might evolve multiple limbs, not just 4, to provide additional points of contact and further distribute weight, enhancing stability and traction. A 6-legged or even 8-legged gait could be common among larger land animals, providing superior balance and weight-bearing capacity in this high-gravity environment. Beyond the visible anatomy, the internal physiology of these creatures would also bear the indelible mark of Kepler-452b's gravity. The cardiovascular system, for instance, would face an extraordinary challenge. Pumping blood against 2.2 G from the heart to the brain, and extremities would require an incredibly powerful heart, far more muscular than any on Earth, capable of generating significantly higher blood pressure. The circulatory network itself might be reinforced, with thicker vessel walls to prevent ruptures and ensure adequate blood flow to all tissues. Without such adaptations, blood would pool in the lower extremities, leading to unconsciousness or organ failure. Similarly, a robust respiratory system, perhaps with more efficient lungs or alternative gas exchange mechanisms, would be vital to provide the energy-dense oxygen required by such powerful muscles, especially within a potentially denser atmosphere. Consider the potential for sensory adaptations. While the thick atmosphere would protect against harsh radiation, it might also make long-distance sight challenging due to haze or scattering, potentially favouring other senses. Hearing could be excellent, with denser air transmitting sound more efficiently. Olfaction, too, might be highly developed, allowing creatures to detect distant food sources or predators through air currents carrying heavier, more concentrated scent molecules. The very way they perceive their world, how they navigate and interact, would be fundamentally shaped by these physical constants. When imagining the food chain, the adaptations would extend to feeding mechanisms. Herbivores, feeding on the thick-stemmed, sprawling flora, would need incredibly powerful jaws and robust teeth to process such dense plant matter. Their digestive systems would have to be highly efficient, extracting maximum nutrients from low-lying, fibrous vegetation. Carnivores, in turn, would be apex predators of immense strength. Their hunting strategies would likely involve ambush or short, powerful charges, leveraging their incredible muscularity rather than sustained high-speed pursuit. Grappling and subduing prey under 2.2 G would require an entirely different suite of biological weapons: powerful claws, crushing bites, and a low centre of gravity to pin their victims. Reproduction and early development would also present unique challenges. Laying eggs, or giving birth to live young, would require careful consideration of gravity. Eggs would need reinforced shells to prevent crushing, and young, whether hatched or born, would likely be incredibly vulnerable in their early stages, perhaps remaining hidden in burrows or within protective structures until they developed sufficient strength to withstand the gravitational pull. Parental care might be extensive, ensuring the survival of few but robust offspring. Evolutionary pressures would favour rapid development of strong musculoskeletal systems in the young, enabling them to move independently sooner. The behavioural ecology of these giants on a heavy world would also diverge significantly. Burrowing might be a common strategy for shelter from potential weather or predators, as excavating and maintaining underground dwellings would offer protection from the surface forces. Climbing trees, if any existed, would be an extreme feat of strength, likely limited to smaller, specialised creatures. Social behaviours could emphasise mutual support in locomotion or defence, where individuals cooperate to overcome the physical challenges of their environment. The very landscape of Kepler-452b, with its largely flat terrain, would influence migration patterns and territorial disputes, perhaps leading to vast, slow-moving herds or solitary powerful hunters dominating expansive plains. Ultimately, these imagined terrestrial life forms on Kepler-452b serve as a powerful thought experiment. They demonstrate that while the universal laws of biology, the drive to extract energy, replicate and evolve through natural selection, remain constant, their expression can vary wildly under different physical parameters. The high gravity of this super-Earth would sculpt a biosphere of immense strength and enduring resilience, a world where life, though potentially vibrant and ancient, would move with a deliberate, powerful grace, fundamentally distinct from the light-footed inhabitants of our own pale blue dot. The sheer alienness of such a world, even while fulfilling the basic criteria for habitability, underscores the incredible diversity the cosmos might hold, reminding us that even a second Earth would be a universe unto itself. From the low-slung, powerfully built terrestrial creatures hypothesized for Kepler-452b, a contentious and captivating question inevitably arises. Could anything truly achieve flight on a world with 2.2 times Earth's gravity? On our planet, the marvel of avian flight, the soaring elegance of an eagle or the delicate flutter of a hummingbird, is a testament to the elegant interplay of aerodynamics, bone structure, and muscle power against a relatively forgiving gravitational pull. On Kepler-452b, this same physical feat would demand biological innovations so extreme, so utterly revolutionary, that they push the very boundaries of our imagination. Many exobiologists, when first confronted with the parameters of a high-gravity super-Earth, would argue that powered flight, as we understand it, would be virtually impossible. The simple physics are daunting. To generate enough lift to overcome double the Earth's gravitational force requires an exponential increase in wing area, muscle power, or both. A bird on Kepler-452b, even if scaled up, would effectively weigh 2.2 times more, rendering its wings useless for sustained flight. Its bones, already needing to be incredibly dense for ground-based locomotion, would make the entire organism too heavy to ever truly leave the ground through flapping. The energy expenditure required for such an endeavour would likely be prohibitively high, making the evolutionary cost too great for any advantage gained. However, the universe often defies our Earth-centric assumptions, and some researchers propose a fascinating counterpoint, a sliver of possibility that hinges on another of Kepler-452b's unique characteristics, its potentially significantly denser atmosphere. If, as hypothesized, the planet's formidable gravity has enabled it to retain a much thicker, more massive atmospheric envelope than Earth's, then the rules of aerodynamics shift dramatically. A denser medium provides greater resistance, which directly translates into increased aerodynamic lift. Imagine trying to run through water versus air. The resistance is far greater in water. Similarly, a denser atmosphere provides more purchase for wings, allowing them to generate more lift with less effort than in thinner air. In such a scenario, where aerodynamic lift could be dramatically increased, the evolutionary pathway to flight, while still monumental, becomes conceivable. Flying organisms on Kepler-452b might evolve truly massive wingspans, disproportionately large compared to their body size, designed to catch and leverage every possible bit of lift from the thick air. These wings would likely be broad, membrane-like structures, perhaps akin to prehistoric gliders like the largest pterosaurs, but on an even grander scale. Imagine wings spanning tens of meters, catching updrafts and thermal currents in an atmosphere that feels almost viscous. To combat the crushing gravity, these creatures would also need extreme adaptations to their body mass. Their skeletons would have to be lightweight, yet incredibly strong, perhaps an advanced form of hollow bone structure, or even a biological equivalent of aerogel, a material with exceptional strength-to-weight ratio. Their bodies would be streamlined, minimizing drag as they push through the dense air. Their musculature, while powerful, would be focused on precise control and efficiency, enabling them to exploit subtle shifts in atmospheric pressure rather than relying solely on brute force flapping. Their flight strategy might bear little resemblance to Earth's dynamic flyers. Instead of agile maneuvering and high-speed pursuit, flight on Kepler-452b could be dominated by static soaring. Picture colossal, slow-moving aerialists, launching from high vantage points if any existed on a flat world, then riding thermal currents generated by the ample stellar energy, much like Earth's condors or albatrosses, but at a more majestic, almost ponderous pace. They would conserve energy by gliding for extended periods, perhaps using subtle shifts in wing angle to navigate the dense air currents. Landing, too, would be a carefully orchestrated event, requiring powerful braking mechanisms and robust limbs to absorb the impact of returning to a world with such a heavy embrace. Predation and survival in the air would also be fascinating to consider. Aerial hunters might be rare, as the energy cost of chasing prey in such conditions would be immense. Instead, we might see scavengers, riding high to spot carrion on the vast flat plains below, or specialized filter feeders, scooping up airborne plankton or spores from the dense upper atmosphere. The very ecology of airborne life would be profoundly different, shaped by the relentless demands of defying gravity. Still, the challenge is monumental. Even with a dense atmosphere, flight under 2.2 G would demand biological innovations far beyond Earth's examples. It would be a fusion of incredible strength and extreme lightness, a biological paradox that defies our immediate imagination. Yet the possibility lingers. If the atmosphere is dense enough, and the evolutionary timeline of 6 billion years has been kind, then some forms of life, with wings and body structures meticulously adapted to a thick, buoyant atmosphere, might still have mastered the art of flight. They would be slow, perhaps cumbersome by our standards, but utterly magnificent in their defiance of one of the universe's most fundamental forces. This exploration of flight on Kepler-452b is a testament to the power of divergent evolution. It reminds us that while universal physical laws set the boundaries, life finds a way to fill every niche, often in ways that challenge our preconceived notions. The image of massive, slow-gliding organisms soaring through a deep indigo sky, their colossal wings catching the light of a distant ancient sun, is one of the most compelling and alien possibilities this second Earth offers, a dream of freedom against a heavy world. Our journey through the imagined ecosystems of Kepler-452b, from its deep blue sky and sprawling oceans to its sturdy flora and gravity-defying fauna, paints a vivid picture of a potential paradise. Yet, science is not merely about marveling at wonders, it is equally about confronting harsh realities, about tempering hope with rigorous risk assessment. Even a world as promising as Kepler-452b, with billions of years of potential biological evolution, faces an array of existential threats, both intrinsic and extrinsic, that could transform a potential Eden into a cosmic wasteland. Assessing these risks is just as critical as dreaming of possibilities, grounding our awe in scientific sobriety. The first and most formidable concern lurking in Kepler-452b's future is the runaway greenhouse effect, a catastrophic climatic tipping point. We've discussed the planet's larger size, its dense atmosphere, and the 10% greater stellar energy it receives compared to Earth. These factors, while initially conducive to warmth and liquid water, create a dangerous vulnerability. If carbon dioxide levels in the atmosphere were to accumulate past a critical threshold, perhaps through sustained volcanic outgassing without sufficient geological or biological carbon sequestration, the planet could trap an irreversible amount of heat. This would initiate a devastating positive feedback loop. Rising temperatures would evaporate vast quantities of surface water, releasing immense amounts of water vapor, a powerful greenhouse gas, into the atmosphere. This, in turn, traps even more heat, leading to further evaporation until entire oceans boil away into space. The ultimate fate in such a scenario is eerily similar to Venus, our solar system's own tragic example of a runaway greenhouse. Once thought to harbour ancient oceans, Venus is now a scorching inferno, its surface temperatures near 403°, 478°, a crushing blanket 92 times denser than Earth's. According to climate models from NASA, if Kepler-452b's atmospheric CO2 concentration crosses this critical threshold, its extensive oceans could evaporate entirely in mere millions of years, a blink in cosmic time given its star's ancient age. This transformation would sterilize the planet, reducing any complex life to cinders and fundamentally altering the chemistry of its surface, turning a vibrant world into a desolate, superheated tomb. The billions of years of biological evolution would be abruptly terminated, leaving behind only the ghost of a once thriving biosphere. Another formidable risk lying deep within the planet's very structure is the potential for intense tectonic and volcanic activity. Earth's internal heat, primarily generated by the decay of radioactive isotopes like uranium, thorium, and potassium-40, drives its plate tectonics and volcanism. This geological activity is a double-edged sword. It is essential for recycling carbon, regulating atmospheric composition, and sustaining life's chemistry through processes like hydrothermal vents. However, an excess of internal heat, perhaps due to a significantly higher concentration of these radioactive elements in Kepler-452b's core, could generate colossal, uncontrolled energy. This might drive relentless, hyperactive tectonic shifts and catastrophic volcanic eruptions on a scale far beyond anything seen on Earth. Imagine a world constantly reshaped by mega eruptions, spewing vast quantities of greenhouse gases and ash into the atmosphere, triggering long-term volcanic winters, followed by intense warming. Violent, planet-spanning quakes would rip apart ecosystems, causing tsunamis across its global oceans and rendering any long-term ecological stability impossible. A planet ravaged by such geological fury would struggle to maintain the delicate environmental equilibrium required for the sustained evolution of complex life. While geological activity is generally beneficial, an overabundance could spell doom, turning a potential paradise into a geological nightmare, a world in perpetual violent upheaval. Finally, there is the silent yet terrifying danger of biological and immunological threats, a risk that arises not from the planet itself, but from the hypothetical notion of interaction. If Kepler-452b indeed harbours life, whether microbial or more complex, its biochemistry would have evolved independently for billions of years, entirely distinct from Earth's. Our immune systems would be utterly unprepared for alien pathogens, viruses, or bacteria, with cellular structures, genetic material, and metabolic processes completely foreign to terrestrial biology. Even accidental exposure during a hypothetical future mission, long beyond our current capabilities, could unleash pandemics beyond the grasp of terrestrial medicine, or trigger severe allergic reactions to unknown compounds produced by alien flora and fauna. This immunological barrier is an invisible yet profound threat. A sobering reminder that the universe hides not only beauty and potential, but also perils beyond our comprehension. Conversely, the threat cuts both ways. We, inadvertently, could become the invaders, a biological threat to any native biosphere on Kepler-452b terrestrial microbes, harmless to us, could prove catastrophically devastating to an alien ecosystem, echoing the tragic history of European microbes decimating indigenous populations and ecosystems upon contact with the Americas centuries ago. The ethical implications of such potential biological contamination are immense, highlighting the profound responsibility that would accompany any future attempt to interact with a living exoplanet. In the grand view, the potential perils of Kepler-452b underscore a fundamental truth of planetary science. The closer a world resembles Earth, the more dangerous and complex it becomes if misunderstood or approached without extreme caution. Life may exist, thriving in its ancient alien forms, but the presence of stable, advanced, or communicative life is another question entirely, one that hinges on the planet's ability to navigate these existential threats over cosmic timescales. Standing on the edge between hope and hazard, one question looms larger than all. Is Kepler-452b truly our best candidate among the stars, or simply a beautiful, tantalizing illusion, a paradise perpetually on the brink? The vision of this distant world is not just a testament to life's potential, but a stark reminder of the fragile tightrope walk every living planet must undertake through cosmic time. Our scientific journey to Kepler-452b, though purely an intellectual voyage, has painted a breathtaking portrait of a potential paradise, a world of deep indigo skies, sprawling shallow oceans, and resilient life adapted to a profound gravitational embrace. We've imagined its ancient flora, its powerfully built terrestrial fauna, and even considered the audacious possibility of flight under conditions that seem to defy our understanding of aerodynamics. Yet, through all these captivating simulations and scientific extrapolations, a single immutable truth persists, casting a long shadow over our cosmic dream, the unbridgeable chasm of 1/400 light-years. This immense distance transforms our second Earth from a tangible destination into an unattainable, beautiful illusion, a perpetual reminder of humanity's current cosmic limitations. To truly grasp the scale of 400 light-years, we must attempt a relativistic analogy. If we were to travel at the speed of the fastest spacecraft ever built, NASA's Parker Solar Probe, which can reach speeds of 690,000 kilometers per hour, it would still take us roughly 4,600 years to cover a single light-year. To traverse the 1/400 light-years to Kepler-452b would demand an inconceivable journey, lasting approximately 6.4 million years. That's a timescale vastly longer than the entirety of human civilization, longer even than the existence of our species. Homo sapiens. It is an epoch stretching back before the emergence of modern humans, before the last ice ages, before our ancestors even walked fully upright. Such a journey is not merely impractical, it is, with any technology currently known or even conceived, utterly impossible. The fundamental barrier lies in the laws of physics themselves. Einstein's theory of special relativity dictates that nothing with mass can accelerate to the speed of light. Even if we could approach it, The energy requirements would be staggering, far exceeding anything our civilization can produce. Furthermore, the immense distances mean that any signal we send to Kepler-452b would take 1,400 years to arrive, and another 1,400 years for a response to reach us. This 2,800-year communication delay renders any meaningful interaction, let alone travel, beyond the realm of practical reality. The very act of observing this planet is akin to looking into a cosmic mirror reflecting the past. We are seeing Kepler-452b as it was 400 years ago, long before our modern telescopes even existed. Our current technological capabilities for interstellar travel are nascent at best. Propulsion systems like chemical rockets or even advanced ion drives are far too slow. Concepts like warp drives or wormholes remain firmly in the realm of theoretical physics and science fiction, with no tangible pathway to realization. Even if we could develop revolutionary fusion or antimatter engines, the sheer scale of fuel required to accelerate a spacecraft to a significant fraction of the speed of light, and then decelerate it upon arrival, is astronomical. The logistics of shielding a crew from interstellar radiation for millennia, maintaining life support, and preserving psychological well-being for generations of travellers represent engineering challenges orders of magnitude beyond anything we have ever attempted. The tragedy, therefore, is profound. We have used our ingenuity, our scientific prowess, to glimpse a world that appears to be a veritable twin of our own, perhaps even an older, more evolved version. We have seen, through the lens of data and simulation, a planet that could harbour sprawling oceans, vibrant ecosystems, and ancient alien life. We have painted a picture of a paradise, a second chance, a cosmic reflection of what Earth might have become or might yet become. But this portrait hangs in a gallery we can never enter. It is a masterpiece viewed through an unbreakable pane of cosmic glass, a poignant reminder of our limited reach in an infinite cosmos. This unreachability is not just a technological hurdle, it's a deep philosophical challenge. It forces us to confront the inherent isolation of intelligent life, highlighting the vast, silent chasms that separate civilizations, even those on potentially habitable worlds. The Fermi paradox, which questions why we haven't found evidence of other intelligent life despite the statistical probability, gains an additional layer of poignancy when we consider worlds like Kepler-452b. Even if a thriving, advanced civilization exists there, separated by such immense distances and temporal lags, our chances of ever knowing or interacting with them are vanishingly small. We are cosmic castaways, floating on our own oasis, able to observe distant shores but unable to cross the ocean. The existence of Kepler-452b, therefore, becomes a powerful parable. It embodies the human drive to explore, to discover, to dream of other worlds, even as it underscores the humbling reality of our current place in the universe. It is a beacon of hope for extraterrestrial life, a testament to the universe's capacity for creating Earth-like conditions, but simultaneously a monument to our cosmic confinement. This second Earth is a beautiful, thriving dream, a testament to what might be, but it will forever remain an unattainable dream, a potent symbol of the vast, silent, and indifferent expanse that separates us from the nearest potentially habitable worlds. The most magnificent discovery sometimes is also the most heartbreaking, leaving us with a profound sense of wonder tinged with an inescapable melancholy. Our intellectual odyssey to Kepler-452b concludes, leaving us suspended between the profound awe of discovery and the poignant ache of an insurmountable cosmic distance. We began with the stunning revelation from the Kepler Space Telescope, a faint signal across 1,400 light-years that heralded the existence of a world astonishingly like our own. We then meticulously reconstructed this distant super-Earth, peeling back the layers of scientific data to imagine a vibrant ancient world, its benevolent sun-like star offering billions of years of stability, its dense, potentially indigo atmosphere filtering the light and moderating temperatures, and its vast, shallow oceans acting as both climate regulator and cradle of life. We dared to envision the bizarre yet beautiful ecosystems that might have flourished under 2.2 times Earth's gravity. The sprawling, robust flora, designed to cling to a heavy world, perhaps exhibiting entirely new colours of photosynthesis. We imagined the low-slung, powerfully muscled terrestrial creatures, each step a testament to immense strength. Their bodies sculpted by the relentless downward pull, and we even entertained the audacious possibility of flight, not as delicate avian ballet, but as a majestic, slow-gliding defiance, born from massive wingspans and a thick, buoyant atmosphere. This scientific simulation paints a picture of a dynamic, living world, an ancient paradise teeming with its own unique evolutionary story, a testament to the boundless creativity of the universe. Yet, as vividly as we have painted this distant world, the core drama of Kepler-452b remains its profound inaccessibility. We grappled with the chilling reality of its potential perils, the ever-present threat of a runaway greenhouse effect turning an Eden into a Venusian inferno, the dangers of hyperactive geology, and the terrifying unknowns of alien biology should contact ever be conceived. But even these formidable challenges pale in comparison to the single, most heartbreaking truth, the 1,400 light-years separating us. This vast expanse, a chasm of time and space, renders Kepler-452b a dream forever beyond our reach, a cosmic what-if playing out on a stage we can only ever observe from afar. This journey to an unreachable paradise is more than just a scientific exercise. It is a profound philosophical mirror. It compels us to confront our place in the universe with renewed perspective. For all our technological prowess, our insatiable curiosity, and our relentless drive to explore, we are for now confined to our pale blue dot. The immense distances, governed by the immutable laws of physics, remind us of our cosmic isolation, highlighting the sheer improbability and preciousness of our own existence. Kepler-452b stands as a monument to life's potential, a beacon in the dark, but also a stark reminder of the limits of our reach, the barriers that may forever divide civilizations across the galaxy. And this perhaps is the most profound lesson Kepler-452b has to offer, a re-evaluation of the home we already possess. Every discovery of a potentially habitable exoplanet, every whisper of a second Earth, paradoxically amplifies the extraordinary significance of our first, Earth, with its delicate climate, its oceans of liquid water, its life-sustaining atmosphere, and its intricate web of biodiversity, is not just a planet among billions. It is a singular, irreplaceable oasis. It is a miracle suspended in the cold, endless void, a haven that has nurtured complex life for billions of years, navigating the very threats of runaway greenhouses and geological cataclysms that loom over distant worlds. The quest for a second Earth, while inspiring, should not diminish our appreciation for the first. On the contrary, it should ignite a fierce protective imperative. Are we truly cherishing and protecting this unique celestial garden that gave us life, that evolved us to even ponder worlds like Kepler-452b? Are we safeguarding its delicate balances against the very forces of climate change and environmental degradation that could push our own world towards a less habitable future? The story of Kepler-452b is not just about the search for life beyond Earth. It is a powerful, urgent warning, a call to look inward. This question, simple yet profound, may hold the key to humanity's future, not among the unreachable stars, but here, on the vibrant living planet that birthed us. Sometimes, the greatest wonder in the universe is not the world we tirelessly seek across light years of emptiness, but the one we already inhabit, the one beneath our feet, the one that is, unequivocally, our only true home. The contemplation of Kepler-452b, therefore, ultimately brings us full circle, back to Earth, to a deeper understanding of its fragility, its resilience, and our sacred responsibility to preserve its singular miracle. The dream of Kepler-452b may be unattainable, but the reality of Earth is a gift we hold in our hands, a gift that demands our unwavering attention and protection.